Can you guys all hear me out there? So I uploaded this PDF file of the spectral data as an announcement. So if you want to check the Canvas announcements, try to download that. We'll go through this that problem today as well after we do some introduction to NMR. And again, I'm not terribly certain how to make this the document camera show up in the shared screen. I'm not I'll probably have to ask like iTech or something. Okay, hopefully everyone can hear me. I think so. Are there any questions before we get started? You should be able to see my keynote slides for today through the shared screen. So what we'll do first, we are basically going to continue on with spectroscopy. So we'll get a little bit more in depth with NMR today, specifically proton NMR. We'll do a little bit of carbon NMR. And then once we go through that, we'll go through that PDF that I uploaded into Canvas where we're where we're looking at a bunch of different data for a single compound, and we're asked to provide the structure. So we'll put our chemical intuition to good use for that, and look at all the data, make sure that it makes sense, make sure that the claims that we're making all corroborate one another and don't sort of violate any piece of data that we're considering. So let's go ahead and look at this slide here. This was pulled from either your current textbook or the textbook we were using before, but it's just a spectroscopy problem. And I have a whole series of slides that basically say, are you Chuck Norris enough? So Chuck Norris is pretty awesome. As you can see, Chuck Norris built the hospital that he was born in. And you can see there's Chuck fighting the great Bruce Lee. So we want to become Chuck Norris and become awesome in what we do. So let's consider these spec problems and see if we can distinguish basically in each of these ones, A, B, and C. How would we distinguish them using the indicated method of spectroscopy? So for A, we have these two compounds and we're asked to distinguish them by proton NMR. So first, maybe in the chat, what main functional group do you see in these two compounds for problem A here? What's the main functional group? So these are esters, and so if you look at them, maybe what you can do now is, or maybe the question I can ask is, what is the relationship between these two compounds? So what relationship do these two have? So one way you can think about answering is first calculate the molecular formula. So Ian says they both have the same molecular formula. Aiden says they're structural isomers. So maybe we'll refine that word a little bit. Instead of structural, we'll call them constitutional isomers. So they both have the same molecular formula, which looks like C4 H8O2. So C4H8O2. So they're constitutional isomers. They both have esters. How many unique sets of proton of hydrogens are there? So unique sets of hydrogens does each have? So what's the total number of sets that each has? So both have 3 unique sets, and then what is the ratio of those sets? Again, the total number in the ratio should equal 8. So some of the early answers are 3 to 2 to 3. So yeah, that's all the same, right? So everything we've done so far, they're constitutional isomers, they have the same molecular formula, they're esters, they have 3 unique sets, the ratios are 3 to 2 to 3. So far, we haven't done anything that differentiates them. So can you, just through empirical research, and that means what you see with your eye, what you're observing, can you think of a way how they're different? What is different about them? If you are given two spectra, how would you assign the structure to the spectra? What's your thought process? So Tenley says the ester is bonded at a different place. Yeah, that's definitely a solid observation that we can use to our advantage. So let me just I'm gonna flip over to the document camera. So I'm gonna sort of go back and forth between the document camera and the screen. So those are the structures, and again, we're asked to differentiate them by proton NMR. So what I'm going to do, I'm going to click over to a different program and sort of continue on this line of thought about empirical research. So see this slide here. The next program that I'm going to bring up it's just called NMR. It's an app that's found in the Apple Store, and this is the developer, Kirill Blinov, I believe is the name. So I think the one that's called Orange NMR you can get for free, and it allows you like to draw like maybe 10 or something structures. So I have a paid version of it, and so that's what I'm going to bring up next. So I assume you all can see this now different window with, it's called NMR. So so my version has this sort of like purple color. And this guy that developed it worked for a company that basically does this sort of software. And so what I'm going to do to help answer this question that you can see in the document camera, I'm just going to go ahead and start drawing. So if I click and I draw basically, so what I've shown here now is ethane, right? So let me just delete that. Okay, so that's sort of what I wanted to start with, was just methane. So look at the chemical shift of both the carbon and the hydrogen. So the top spectrum is proton or hydrogen. The bottom spectrum is the carbon. So when I highlight that an sp3 hybridized carbon occurs at about -2 in the carbon NMR, then the hydrogens bonded to it are about 0.23. So I'm going to start modifying this. So there I've drawn ethane. So now I'm going to put in the double bond for the ester. So here is the compound. So I'm on the doc cam, so it's this compound here. So notice when I highlight, I'm going to go over to this peak here at 1.20, the peak to the farthest right. So it's saying the chemical shift of the protons there are 1.20, and the highlighted carbon there is at 14.4, and again, that's the chemical shift. So I'm just going to go over, I'm going to highlight that one now. So that peak occurs at 1.97. So if I highlight that the carbon now, you see it highlights at 21. And then finally the last peak at 4.10. Then I'm going to hover over, and I see that carbon occurs at 60.4. So what you can see, again, I'm on the doc cam, the chemical shift for proton lies between 0 and 10. For carbon, lies between 0 and 220 ppm. And what this means is that these functional groups occur in different regions of these spectra. So again, the sp2 hybridized carbon, that occurs at 170. So now I'm going to modify the structure as it's drawn. Draw the other one. And then we're going to go through the same sort of exercise. So now this group here is at 1.10 parts per million. If I highlight the carbon itself, that carbon's at 9.2. If I move over to the next signal, that's at 2.36. The carbon is at 27.2. Then finally, the last signal, that's at 3.76. And the carbon itself is at 51. The sp2 hybridized carbon is at 173. So Hannah's asking, where did 0 to 10 and 0 to 220, where did these numbers come from? These are just the scales that these spectra occur in. So the proton NMR occurs from 0 to 10 parts per million. The C13 NMR occurs from 0 to 220 parts per million.
Is that just that you showed, or is that for all proton and NMRs?
This is for every single one. This data will always occur in these regions.
Okay.
So remember, like IR, when you were reading it, was say 4,000 to 400 reciprocal centimeters. So that's how the spectra always look. So Katie's asking about the app. You do not have to buy this app or download it or anything. I'm just using it as a tool to show you how things are different. So when we're asked to differentiate these by proton, notice really the big thing, which I'll highlight in red. So see this CH3 group, how it's directly bonded to the carbonyl. So that occurs at 1.97. Now you have a CH3 group here, which is bonded to oxygen, and that occurs at 3.76. So what we are aiming to understand is, even though you have, say, CH3 group here and here, the chemical shift is different, right? Then in this molecule, you have CH3 bonded to oxygen versus CH3 bonded to another carbon. So notice how those chemical shifts are different. So as I'm asking you these questions about uniqueness in carbon and proton, we're drilling down even further now to classify, okay, this CH3 group is bonded to a carbonyl. This CH3 group is bonded to a CH2 group, therefore they're different. They occur at different chemical shifts. So we're going to go through, in general, where do these functional groups occur on the spectra? And when you're interpreting these two types of spectra, how can you start to figure out what functional groups are present? And again, we'll look at a problem where we consider all of this data and propose a structure. So let's do this one here, part B, where you have to determine the unique C13 and unique NMR signals. So again, these are all constitutional isomers. So for the one that my mouse is below, how many unique carbon signals would you see for this one where my mouse is circling now? So I'll give you guys a couple more seconds to throw your responses in. Again, the more I encourage you all to sort of respond, regardless of how fast you see responses showing up in the chat. Again, this is your experience, your learning experience here. So don't be intimidated if you see a response come up pretty fast. Take some time to process it and put your response in the chat box. So I see some answers that say symmetry, and yes, there is definitely symmetry in the molecule. So let's determine, you know, we had a lot of initial responses of 6, but then we have some that are different. So let me draw out that compound. So there it is. In this class, again, I'm not really about math or any really hardcore mathematical concepts. It's so let me just repeat that. So again, there's some responses in the chat box about symmetry, and you know, in this course, we're just going to consider the development of chemical intuition. We're not looking at hardcore math, so there is symmetry. So symmetry is usually the easiest thing to think of as like a mirror plane. So here's the molecule. If I draw a mirror plane, which I'm going to do in a dotted line, so consider this red dotted line is a plane perpendicular to the sheet. And so what that means is that these carbons sort of mirror each other on each side of the plane. So if I start here, I have a methyl that mirrors this methyl. So we have another methyl, but these methyls are the same sort of due to their own local symmetry. So instead of having 1, 2, 3, 4, we basically can reduce that to 1 because they're the same here and then they mirror each other. So I'm just going to put like a dot. So those are all the same. Then we have a methine and a methine. So maybe I'll put a little square. Those mirror each other. Then as we move in, we hit this sp2 hybridized carbon. That's different. CH3, CH, this has no hydrogen, so I'll put a little triangle. So we're up to 3 now. Then let me go this way. So I converge onto the mirror plane. So maybe I'll put a little rhombus. So 1, 2, 3, we're up to 4. So let's go back down this route. We went that way, let's go this way. We have an sp2 hybridized carbon with an H. So I'm sort of running out of shapes here. Maybe I'll do an asterisk. So those mirror each other, that's 5. And then we're on the last one here. I'm going to use sort of the dot again. So that's 6. So this one has 6 unique carbons. What about hydrogens? How many unique sets of hydrogens does that one have? So I'm inclined to say 5 for the following reason. So the CH3s of the methyl, that's 1. The methine is 2. This does not have 1. This is unique, so that's 3. That's unique, that's 4. This is unique, that's 5. Yeah, sorry, the plane that I drew with the dotted line, there's a hydrogen there. So if you missed that, that could be the 5th. So 1, 2, 3, 4, 5. So what should we write for now the ratios? Of those 5 sets, we need to write we need to write 5 numbers. So each set has a unique number to it, right? So what number should we put in there? So we see some early responses. Again, make sure you're trying to do this on your own as well, because that's really where you learn the material. So yeah, if we consider the methyls, we have 3, 6, 9, 12. Then the methynes, 1, 2. Then we're now in the ring. So again, we had 3 of them that are in the ring. We have these, so that's 2. Then we have 1 and 1. And so I've been using the word ratio, which it's fine because that's our empirical observation. Another word that we can use that we'll see today is called integration. So ratio or integration. Sarah's asking, do you have to put them in a certain order? I would say in the strictest sense, you probably could, but just in terms of the exercise, not really, because the order you might want to put them in is how you would read them in the spectrum, but it would be really hard to do that sort of without a deeper understanding yet of chemical shifts. So just as long as you have the right numbers, it really doesn't matter what order we put them in. So how did we count the 12? So we have 1, 2, 3, 4 methyl groups. They each have 3 protons. That gets us our 12. So 3, 6, 9, 12. So let's go on to its constitutional isomer. what is, how many unique carbons does this one have? So we have some 3s, some 5s, some 6s. Maybe take a deeper look at this molecule. So maybe I'll type something in the chat here that maybe you'll understand now, or maybe it'll take some thinking. So when you look at this molecule and you determine the molecular formula, you're coming up with, say, 12 total carbons. But you're not going to see 12 signals in the carbon NMR, and that's due to the symmetry. So that's what we're figuring out now. So I see Ian and James put down 4, and 4 is the correct answer. So how did we come up with 4? And again, in the red marker here, so if you're interested, this is called a Stabilo Pen 68. If you want, and send you the website where I got these. So there's in this one, there are 2 axes, as Ian points out, 2 axes or planes of symmetry. I actually want to say the word axes is fine. Yeah, we'll go with that word. So we can draw here. That's one axis or plane. And then probably why you're not seeing the other one is just how the molecule is, maybe I've drawn it. There's another one here. So the one axis or plane reduces the count from 12 to lower, and then the second one reduces it even further. So where are the 4? We have 1, 2, 3, 4. So if I number them all sort of with that scheme, so there's again a 1, 1, 1, 2, 3. Oops, sorry, 3. This would be a 4, and a 4. So all the 1s are the same, all the 2s are the same, the 3s are the same, and then the 4s are the same. So again, the value in this exercise is like I've said before, many of you are not going to study organic chemistry. Only a few of you are probably going to go into biochemistry. But the value in these type of exercises is the empirical observation and learning how to think about solving problems. So we've reduced the carbon count to 4 unique type of carbon. How many unique type of hydrogens are there? Okay. So unique type of hydrogens in this molecule. So I see 3 showing up in the chat. So again, that's right. Could you mark the unique H's? So yeah, the unique hydrogens. So I'll put some, so unique hydrogens, the 1s, those are methyl groups. That's one set. Now the methynes. And then the 4s on the aromatic ring, we'll mark those all as sort of triangles here. So we came up with 3 unique sets, and now we should report 3 numbers. So what should those numbers be? So Alexis is asking, these are constitutional isomers. Notice the relationship between this group here on the ring. It's 1, 2, 3. Now it's 1, 2, 3, 4. So they're separated. So we have an early response here, 12 to 2 to 4. So 12 to 2 to 4. Again, it doesn't really matter what order we write those in, just as long as we're getting the correct numbers. So if you don't mind looking back at the slide deck now, I've drawn the first one in, and I apologize that the spectra aren't terribly large. You sort of have to get out your reading glasses here. So this is the first one. And so I'm going to show you the 6 type of carbons in the lower spectrum. We're just going to count. So watch when I highlight, if you can see this little magnifying glass on the lower spectrum, that's the carbon. So see the chemical shift, 24.1, that's the methyl groups. 34.3, that's the methine. See how their chemical shifts are much separated because they're sp3 hybridized? Now when I move over, I'm getting into the aromatic ring, so these occur in a different region. So we're up to our 3rd unique carbon at 123.8, 124.8, 128.3, and then 148.8. So that gets us, that's where you see the actual signals in the carbon NMR. So you came up with 6, and now you're visually seeing them. So 1, 2, 3, 4, 5, 6. So in the top spectrum, I'll do the same thing. There's the methyl groups are highlighted. So there's your 12, then your methine, that's your 2, then you have 1 on the aromatic ring, the second one on the aromatic ring, and then your other 2. So that's your total of 5 that you see, and then there's this ratio. When you actually look at the data, it's called an integration. So let me show you, let me draw the other one now. So in the bottom spectrum, we said there were 4 carbons. So we can see them, 23.9. That's the methyl, 33.7 is the methine. 126 146.3, those are the carbons bearing the hydrogens, and then 146.2 are the carbons bearing the ring substituents. So that's our 4 we came up with. Then the top spectrum shows our 3 sets. There's the methyls at 1.27, 2.77 is the methine, and then 7.15 are the aromatic protons. So everything you did through empirical observation, what you're seeing on the slide deck now is the actual data. So that's the connection that we've been making through the uniqueness throughout the semester. Any questions before we move on? We're going to dig a little bit deeper into protons specifically today. So here on this slide, it's called NMR Basics, Functional Group Locations on the NMR Spectrum. The top spectrum is a proton running from 0 to 12. I said 10 is typically the region. I'll explain why it goes to 12. The bottom is your carbon NMR. That goes from 0 to 220. So delta is the symbol that you commonly see, and the unit is parts per million, or ppm. So typically, when I read NMR spectrums, I'm starting at this region at 0, and then I'm reading to the left. So why is that helpful? So in this region from 0 to 1.5, that's your fully saturated carbon, your sp3 hybridized carbon bonded to hydrogen. So that's fully saturated. That's where you'll see that sort of functional group occur. The next region, 1.5 to 2.5, these are also sp3 hybridized carbon bearing hydrogen. So again, in this top thing, we're looking at the proton specifically. That's what's highlighted in blue here. So, but these hydrogens are located on allylic. So allylic, this is a term you'll need to know. An allylic carbon is one directly bonded to a double bond, whether it be an alkene or a carbonyl. And so what you're going to notice as we move left is the environment of the hydrogen changes in terms of the chemical shift number as things are added to the carbon. So from 2.5 to 4.5, the carbon now has a heteroatom bonded to it. So really what we're seeing is on this spectrum where different functional group hydrogens occur. So saturated, allylic. What I mean by heteroatom is the carbon is bearing a heteroatom, and that shifts the proton. 4.5 to 6.5, this is called vinylic. So notice the difference between allylic, the carbon's sp3 hybridized, and again, we're looking at the proton signal, carbon sp3 hybridized, vinylic, the carbon is sp2 hybridized, aromatic, the hydrogen's bonded directly to an aromatic ring. At about 9, you see the aldehyde, sp2 hybridized carbon H. You're seeing the hydrogen. And then for carboxylic acids, this hydrogen typically occurs about 12. So any questions on that? So maybe what I can do is try to show you with this drawing program. I'm running out of like screen real estate here. I'll start a new one. The reason I like this app that I'm using now is it can demonstrate the following pretty easy. So I'm going to put in what I've drawn here is now, again, we're just focusing on the carbon for now. Remember how I said from this region, from 0 to 1.5, those are hydrogens bonded to fully saturated carbon. So watch what I do as I sort of manipulate this structure. So I'm basically going to make this now a double bond. So you see this carbon here, it was about 0.2, how it now shifted into this different region. And that's basically because we bonded this other group now to that carbon. So as we change the environment, you'll see these things shift. So let me change, see this, these are both the same. See how it's at 0.86. I'm going to change this to an oxygen now, and watch that shift move. So see how the methyl group is now at 3.48. So when it was just bonded to other carbon stuff, it was like over in this region. The heteroatom is basically pushing it away from 0, increasingly towards 10. So what if I'm going to change this back to carbon. Watch this shift now. I'm going to make both of these sp2 hybridized. So look at the shift now, it's at 5. Because the hydrogens are now vinylic, so they're sort of this functional group now. So I'm going to watch it shift again when I pull this out to an aromatic ring. So now they're at 7.29. So what you should take away from this demonstration is that you're considering the bonding environment of how things shift away from 0 increasingly towards 10. And so that tells you, it's an indication of where these hydrogens are, what functional group they're participating in. Any questions before I click off onto another slide where we can really get in depth for this? So again, you can unmute yourself or throw a question in the chat. I definitely encourage you to ask as many questions because most likely your peers have the same sort of questions. So in this next series of slides, I want to dig a little bit deeper into things that you're obviously seeing with your eyes, but I want to ask you questions. Hopefully we can understand now why these peaks occur in different regions. So we're specifically going to look at this molecule, 2-butanone. So on this slide, it's called signal location and assignment. So strategy and key concepts. These numbers in red are numbers that are assigned through just naming the compound. So what I've done to name this, I counted the carbon chain. There's 1, 2, 3, 4 carbons. Since there's 4 carbons, it's a butane derivative. There's a carbonyl at position 2, so it's a ketone. And the number 2 is telling you the location of the carbonyl, so 2-butanone. That's what those red numbers mean. So down here, the chemical shift. And as we go through this verbiage, it's all in this table here. So let's look at both at the same time. Again, we're reading from right to left. We run into this peak here at 1.5. That's the chemical shift. That's the unit in parts per million where the signal is located on the x-axis. So we're at 1.5. The number in blue is called the integration. It's the number of hydrogens associated with that signal. as I said before, this is equivalent to the uniqueness activity of determining the ratio. So that signal belongs to 3 hydrogens. The group is the specific type of group that gives rise to this peak. Because the integration is 3, that's telling us it has to be a methyl group. So 3CH3. The functional group is a general description of the hydrogens associated with that carbon. This determines where the chemical shift will be. So because we're at 1.05 and we look at the different sets, there should be 1, 2, 3 sets. This one is most different than this one and this one. So I'm calling that an alkane. And I'm assigning it to this group here, 4, this position. So how did I come up with that? Again, if we go back here, this is an sp3 hybridized carbon. So sp3 hybridized carbon has 3 hydrogens, so it should occur in that region. So that's what I mean by assignment. So I've assigned the peak at 1.05 to this position 4, and again the 4 is coming from the nomenclature. Now we're reading right to left. This is the next signal we run into at 2.10. The integration is 3. That tells us it's a methyl group. Now it's different. If you look, we've assigned this CH3 group. We only have 1 left. We know it's this one because that's a CH3 group. It's sp3 hybridized carbon, but it's allylic. So that's why the chemical shift is different now. So we assign that to position 1. So again, the allylics are different. So we've moved farther away from 0 because the electronics of the system have changed. So we've assigned positions 4 and 1. There's only 3 unique sets, so that leaves position 3, which occurs at 2.4 parts per million. It integrates to 2. That's what the blue number is, so that has to be a CH2 group. It's also allylic because it's right next door to the pi bond. And we assign that to this position here. So again, the total number 3 plus 3 plus 2, that gets 8. That's the total number of hydrogens, and we said there was 1, 2, 3 unique sets. Does everyone follow the logic so far? So Christina, yes, there are 8 total hydrogens. So 3, 4, 5, 6, 7, 8. So again, we're going to dig deeper, and that's really what organic chemistry is about. There's a concept, but it's not just knowing and regurgitating that concept. It's really understanding it and applying it to problems that we're analyzing. So I'm gonna go on to this next slide, and we're gonna dig a little bit deeper now. So this was signal location and assignment. So again, location, where it occurs on the spectrum, the assignment, which sort of location on the molecule does that peak belong to? So this one's called signal peak shape. So notice it's in green now, and I've written some words associated with each signal now. So the table is the same as before, but I've added another column. So the chemical shift at 1.05 integrated to 3. It's a CH3 group. That's an alkane. We assigned it to carbon 4. Now I'm using this word multiplicity. in green, I'm calling this peak a triplet. So I've counted of this unique set, the signal has 1, 2, 3 sort of different heights or attached to it, right? So 1, 2, 3, I call that a triplet. The next peak at 2.10, I'm calling a singlet because there's only like a single peak associated with it. Then the final peak at 2.4, I'm calling a quartet because I count 1, 2, 3, 4, a quartet. So those are some new words, multiplicity. So why do these signals look different? Does anyone know what band this is? Maybe not. You probably weren't born in the 80s, but so these peaks all look different, right? Why do they look different? Do you see a relationship that would give rise to the number of hydrogens and the words in green called multiplicity? So the band is called Roxette, and the song is She's Got the Look. So why do these peaks have the look? You know, why, if they're all associated with hydrogens, why do they look different? So Taka and Max say it's the environment, and they're surrounded by different neighboring carbons. So yeah, their environments are all different. Can you maybe specify a little bit more? So neighboring hydrogens, yeah, that's a little more specificity. So Mac is saying they have different neighboring hydrogens. And so perhaps the easiest way to understand it first is looking at this peak assignment of 1. So this peak assignment, and again, 1, that red number in red is the number assignment for nomenclature. That's just the position on the carbon chain. So we said this integrates to 3. That's where the blue number comes from. There's 3 hydrogens. But the peak is called a singlet. And according to what Mac is saying, how many neighboring hydrogens are on this carbon? So how many hydrogens are on carbon 2? So there's none. But we're calling the word a singlet. So how do you think we would arise at singlet? If this has no hydrogens and we're considering the neighbors give rise to the word in green, what sort of equation could we develop? So you always add 1 to the number of neighboring hydrogens. So yeah, exactly. M plus 1 or N plus 1, however, whatever sort of letter, it's the number of neighboring hydrogens plus 1. This has 0. Again, this singlet assignment is for this peak, but the shape of that peak is determined by the neighbors. There's no neighbors here, so 0 plus 1 is 1. That gets you this singlet. Now let's consider this peak here, where we assign this triplet belonged to this methyl group. That integrates to 3. Why does this methyl group look like a triplet? How many neighbors does this have? So yeah, it has 2 neighbors, right? Carbon 3 has 2 hydrogen neighbors. So 2 plus 1 gets us 3. The word for 3 is triplet. Now we do the same thing for position 3. There's no neighbors here, 0. there's 3 there. So 3 plus 1 is 4. The word we're going to use is called a quartet. So I'm clicking over to the next slide here. I've added 2 more columns for each. So I've analyzed for the triplet, the immediate neighbors, there's 2. The n+1 rule, that gets you 3. For the singlet, there are no neighbors. n+1 is 1. For the quartet, there are 3 neighbors. 3 plus 1 is 4. That gets you 4. Any questions before we move on to the next slide? Again, we're layering these concepts, so we're going to get a little bit deeper. I'm going to ask you another question. So again, we've talked about chemical shift, that's the location. The integration, that's the ratio. What type of group? The functional group, so why it occurs on that region in the spectrum. The actual assignment according to the nomenclature. The multiplicity, the numbers, and the n+1 rule. Yeah, I'll have a separate lecture screencast on this as well. So my next question to you is, again, we've sort of determined why the peaks look different, why they have the look. But what about these words in purple now? Signal peak height ratios. So if you look at, let's start to the right here for the triplet. Look at the ratio of these sort of peaks in the triplet. If you were to measure this, and you can kind of do that according to these rectangles. So say this is maybe 1, 2.5. So I'm counting these like rectangles here, right? 1, 2, 2.5. And so the tallest one is 5. So you get 1 to 2 to 1, and that's the measurement from the baseline to the top of that peak. So 1 to 2 to 1. The singlet, there's only 1, so that's 1. The quartet, if you measure, that's 1 to 3 to 3 to 1. How do you think, why do you think that arises? If you've done the reading, or if you can recall from maybe some math course that you've taken, how do you think you get these ratios for these different sorts of multiplicities? So Max says Pascal's triangle, and so I know we're sort of running short on time, but give me an extra minute. So yeah, it is Pascal's triangle, and I'll cover this in a lecture screencast. So Pascal's triangle is this thing here, where you're starting at 1 at the top, and then as you go down the sides, those are always 1. So in your 0th row, that's 1, that's a singlet. Your first row, that means you have 1 neighbor, that gets you a doublet. The ratio is 1 to 1. The second row, so again, we're starting at 0th row, and the reason I did that is just to correlate to the number of neighbors. No neighbors, 1 neighbor, 2 neighbors, 2 neighbors, 2 plus 1, that gets you your triplet. The ratio is 1 to 2 to 1. Where do you get this 2? So again, there's always 1s down the sides. This number is the sum of these 2 numbers. 1 plus 1 is 2. Third row, that's 3 neighbors, 3 neighbors. 3 plus 1 is your quartet, so that's where you get these 4 peaks. 1, 2, 3, 4. 1 plus 2 is 3. 2 plus 1 is 3, so 1 to 3 to 3 to 1. So that's where we got these ratios of the peak heights too. So I know we're short on time. There'll be a lecture screencast on that. When we start Monday, we'll go over this spec problem. I posted the PDF in a Canvas announcement, but what you can do in the meantime is look at this. This is all the data for one compound. See if you can put all this data, synthesize it together to propose a structure. And then Monday we'll go through this where we consider everything that we've just done in the preceding weeks, where we put it all together. So again, please start working on your homeworks. If you have questions, shoot me an email. I'll try to be responsive within a couple hours. But other than that, I'm going to go ahead and end the screencast. Again,